Okay, so the next thing that we're going to do is we're going to write some code just to demonstrate the basics of using pthreads. We already had a more sophisticated example using sockets, but I think I want to go back to the basics to make sure you get an idea of, just with a real simple program, how pthreads work. All right, so the first thing I'm going to do is copy the code. Well, I'll make dir. We'll call this the singing pthread example. And then we'll copy the code from our dispatcher worker problem here into singing pthread, and then we'll go into singing pthread. And there's some changes we have to make. We really need to, we just need to get the basics in from the server and carve it up, and we'll be good to go. Actually, you know what? I just changed my mind. This is too complicated. Let's get rid of this stuff here. We'll just start from scratch. All right, so we'll copy the, it looks like there's a main, we'll just copy it from Hello World. We should be able to start there. Okay. All right. All right, here we go. Okay, let's just start simple. That's a good way to do things. All right. So if you're going to use threads, what you want to do is you're gonna have to include some pthread stuff. But I just want to create a real simple program to start. All right. So here's my program. I'm gonna say cout sing it threads, and then I'm gonna write a for loop. So for int I equals 0, I is less than, let's have it go, I don't know, I is less than 10, I plus plus. All right, and what this thread is going to do is it's going to do a duet with another thread. So the main thread is every 5 seconds, so we're going to cause it to sleep for 5 seconds. Every 5 seconds, we're going to have the main thread say cout wop. So this is kind of aligned with, do, and then wop. So there'll be one thread that's going do, and then the other thread is going to do wop, but they're going to do it at different intervals. So the main thread's going to occasionally sing wop. The other thread, this thread that we're about to spin off, is going to say do or sing do more often, right? Okay, so that's the idea. So we want to create a second set of code that's going to handle the thread that says do or sings do more often. So what we'll do is we'll create that right up here above the main. And the way you declare this using pthreads is you declare the return type to be void star, and I'm going to call this thread do because it's doing something, and it takes a void star parameter as an argument, but we're not really going to use that parameter right now. We'll definitely use it later. All right, and so this one is also going to work kind of like the main program, the main thread. Let's try that again. Just want to copy and paste this. There we go. But instead of sleeping every 5 seconds, it's going to sleep every 1 second, go to sleep for 1 second, and then it's going to say, do, just like that. All right? So we're going to have two different threads that are executing. One is the main thread that's going to say whop every once in a while, whop, whop. And we've got the do thread that's going to be saying do at a much higher frequency. And the way we're controlling the frequency of their reports is that the do is going to report a do every 1 second, and the WAP is going to report the WAP every 5 seconds. Yes. Tell her I'll have to call her back.
All right. Brandon said he has to call you back.
Okay. So there we go. Now this doesn't quite work yet because we haven't actually created the P thread to make it work, but this is the idea. We basically have two separate methods. They're going to be executing in different threads. One's going to be executing in the main thread. The other is going to be executing in sort of like a child thread that's spun off from the main program. All right, the mechanics of getting the thread to work are the following. So the first thing we're going to do is we're going to create a pthread data structure. And we're going to call that pthread underscore t. And we're going to give that a name of TID. This is the thread identifier. So when we create the pthread, the thread identifier will get populated, and the main program can use that thread identifier to do stuff. Okay? So the second thing we're going to do is create the pthread. And to do that, we're going to call a method called pthread create. Pthread create takes a couple of arguments. The first argument is the address of the thread identifier's data structure. That will then get populated with information from pthread create about the child thread that's gotten created. The next argument are some configuration parameters, which often get set to null. The next argument is the name of the method that's going to execute independently of the main thread. So in this case, the name of that method is do, D-O-O, our do singer. And then the final parameter is an argument that you can pass into the do method if you want. In this case, we're not passing any arguments in, so we're going to put null there. So the moment this pthread gets executed, the do thread or the child thread will spin off and the code in do will start executing. All right? Now, there's some control that we have here that's good to do when you have these threads. So one thing is, rather than letting a child thread just exit, it's better to have the child thread exit using something called pthread exit. This means, hey, the thread exited normally. The reason why you want to do that is that threads have some resources that are allocated to it by the operating system. If you don't do a pthread exit, those resources may not be cleaned up. The other thing is we can control when the main program ends. If we don't control when the main program ends, then after this for loop terminates, the main program will simply end. But what we'd like to do is have the main program wait until the do thread is done executing itself. So we want the do thread to finish executing before the main thread exits, all right? So we could have a race condition where the main thread gets its work done and then just ends, and the do thread goes, what? And then the whole program shut down. We don't want that to happen. So the way we can do that is we can make the main thread wait by doing something called pthread join. So pthread join says, hang out main thread and wait for the thread that's identified by TID to finish. Well, the thread that's identified by TID is the thread that was created when this TID data structure was populated, and that's the do thread. So when do exits, pthread join will return, and we can continue executing. And we'll say that was mighty fine. Okay. Now if I do the math for this, it's going to take 50 seconds for this to execute, and it's going to take, looks like, 10 seconds for this to execute. So maybe what I'll do is increase this by, let's make this 20 seconds. And instead of having this go to 10, we'll have it go to 4. So this loop's going to execute 4 times. 4 times a sleep of 5 seconds means it'll take a total of 20 seconds for this to execute. And this loop up here is going to execute 20 times, but 20 times 1 second of sleep means this loop will take 20 seconds to execute. So basically, the main thread and the child thread running do are going to finish executing at about the same time. Now, which one's going to finish first? I have no idea. That's why I have this pthread join down here that guarantees that if the main thread finishes first, the do thread will get a chance to finish executing before the main thread exits. If the do thread finishes first, that's not a problem. It's going to finish, and the main thread will finish what it's doing. It'll call pthread join and find out that the do thread finished executing, and it'll be done as well. Okay, so I don't remember all the includes that we need. So let's do this. This always happens when we're making programs. I'm going to copy the, well, let's cat the make file that's in, what would we call that, dispatcher. Oh, that hiss is really annoying. I don't know if you guys can hear that, but on my headphones, it doesn't sound so great. Okay, so it looks like I need some flags here. I'm just going to grab this code here, and I'm going to put it in this make file for singing pthread, which is a much simpler make file. Okay. And we also need to know the stuff that we need to include for pthread. So I'm going to cat dispatcher worker again. Ouch, I hope that doesn't hiss like it does for me. And we're going to or display server.cpp. I just want to see the include information here. Okay, I have to include pthread.h. Okay. So we're going to include IOStream and include pthread.h. And we don't really need the main here, so I'm just going to get rid of that. And I'm going to get rid of the main.h here. And I'm wondering if there's anything else that we need here. Man to sleep. Does sleep need anything? And 3 sleep. There we go. Yeah, we got to include this to get sleep to work. So we're going to have to add that. Okay. All right. I'm going to see if I can silence that noise because that is really annoying. No audible bell. Good. I'm sorry. Hopefully that won't torture you anymore. Okay. There we go. Okay. Yeah. Much better. All right, let's make it. See what we end up with. Cool. So we made everything, we included the right things, and now we're ready to run it. So remember, when I run this, you're going to see something kind of cool. Let's just, you're going to see a worker thread, or sorry, a child thread saying do, 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 do. And then every once in a while, you'll see this WAP occur. And you have to remember that the way this is working is two independent threads are executing this program at the same time. All right, so here is the child thread going do, do, do. Oh, then now the parent thread, the main thread just said WAP. And there's the child thread, and there's the main thread. And so they're not really taking turns. They're just grabbing control and outputting stuff to the terminal. And it looks like that what happened here is that the main thread printed out WAP, and the child thread was not done yet. The do thread was not quite done yet. And so the main thread blocked, waiting for the child thread to finish. The do completed, and when that do was completed, the last line of code in the main thread, which was that was mighty fine, got printed out. All right, so that's pretty cool. All right. What do I want to say about Pthreads? What's some further information that I want to give you about Pthreads? Well, I think it's worth understanding a little bit about how they're created in Linux, because every operating system has its own idea about how to manage threads. So to do that, I think what would be useful is, well, actually, it's kind of an interesting experiment. Why don't we just do an observation here? Okay, if I type PS right now, PS says, give me a list of the running processes. And what you see here are two processes. One is PS. That's the PS program itself that's getting run to display PS. So it's a little weird, but cool. And then second is bash. So bash is the shell prompt that's right here that's waiting for me to type in commands. So when I type PS, that is the list of the processes that are running in under my current shell. All right. If I type PS minus ELF or minus EF, you're going to see all of the processes that are running in this system. There are quite a few. Okay. Quite a few. So what we want to do is we want to take a look at what happens when we run main. And what I want to do is I want to show you what things look like when main is being run. All right, so I'm going to run main, and now the two threads are executing, and I want to hit Control Z for a second. And what Control Z does is it says, hey, pause things in that process, in the main process. Just basically freeze the process. So we've frozen it for a moment, and now I want to type PS. Now this is really interesting, right? We've got main, PS, and bash. Let me do foreground and have it run. I'll hit Control Z again. I'll do a PS, main, PS, and bash. Now, it appears as if there's a single program running, single process running, but actually in Linux, there isn't. I've got some notes here. So what I want to do is show you this with a little more degree of information. So PS minus EF grep main. Maybe it says ELF, so let's try putting an L there and see what happens. Ah, there we go. Okay. So with a little bit of teasing, we're getting Linux to reveal some secrets. We actually have two main programs that are running, this one and this one. But what's interesting is that they both have the same process ID. The process ID for the main program is right here, right there. Okay. And so how is that possible? How can we have two processes with the same process ID? And this gets into the explanation of how Linux chooses to implement threads, Pthreads in particular. All right, let's let this finish. So I'm going to just bring up a text document in here, and then we'll edit that. All right, cool. That was mighty fine. So Emacs notes.txt. Okay, so Linux, pthreads, and threads. All right, so the first thing you should know is that Linux does not support low-level threads. These have a special name. They're called kernel threads. So what that means is that there isn't anything specifically in the Linux operating system that has direct support for threads. So if you ask for a thread, is there something in the operating system that automatically gives you a thread that you can work with? In Linux, that's not the case. But yet Linux does support this pthread system. So how does it do it? Okay. Instead, Linux supports something called a lightweight process, or LWP. And here's how you create via something called clone. So let me explain how this works. Underneath the covers, when you call pthread create, so pthread create calls clone. All right, clone, oops, works like fork, but, so clone works like fork, but, so what does that mean? It kind of works like fork, so we create a new process, but it's different. Or I say in a special way. The new process shares the memory, with the child, with, with the parent. That's the best way to say it, okay? Or, sorry, so I don't like the way I phrase that, so I'm gonna rephrase that. So we're gonna say the parent shares memory with the child seamlessly. All right, so what does that mean? Well, the code, the static data, the heap, all of the file handles are shared. The registers and the stack are not shared. And I'm going to put a little asterisk here. Basically, from the moment you do the pthread create, which triggers the clone, both the parent process and the child lightweight process, they are both sharing code static data heap and the file handles, all right, file data structures. And it is possible for the child to get access to information on the parent's stack. It's a little weird, but it is possible. But generally speaking, you want to think about the parent, which initiated the pthread create, and the child process, which is executing the pthread create thread as having independent registers and stack. So the OS, so Linux, views these two processes as independent, but since they share data or share memory, they really aren't independent. All right, cool. So that kind of explains how Linux approaches threads and pthreads. Now, there are other operating systems that have a different approach. So those operating systems, so some operating systems actually have support built into them for low-level threads. They're called kernel threads. And those operating systems, if you were to do a pthread create, the pthread create would map directly onto an operating system low-level kernel thread. All right, cool. All right, I want to take a look at another example of using pthreads. And this one is a pthread race condition that goes horribly, horribly wrong. All right, so yeah, let's write a little bit of code to trigger this. All right. Well, I think we'll stop and then I'll give you the race condition example in the next video.